One of the questions that gets asked a lot is how does one know a solution of an ODE by inspection? Sometimes you'll see in a textbook, the solution to the following differential equation is trivial. It can be done by inspection. And usually the equations are of these forms, so either 1 or 2, and the solution for 1 is y equals a e to the k t, and the solution to 2 is y equals a cos t b sine t. So note the two constants of integration for a second order equation. Let's actually put a frequency in there as well. So let's make it slightly more complicated but more general. There, I've added an omega in there. And a lot of people get confused as how these equations can be, the solution can be recognized so quickly. With equation 1, essentially what this says is that the derivative is proportional to the function itself. There's only one function that does that. It's the exponential function. And that's basically by definition of, or one possible way you can define exponential. You can go through the usual, this is a separable equation, so you can go through the usual steps. You can write that as your equation, and then you can integrate both sides. You can invert this function. Using our exponential laws. One can think of the absolute values as either giving a plus or being a multiplication by plus or minus 1. So if the argument of the function's negative, then you multiply by minus 1. If the argument of the function's positive, you multiply by plus 1. That doesn't really matter because this thing here, this e to the c, plus or minus e to the c, it's a constant. So we write things like a e to the kt, right? Where a is our constant of integration. So that's if you like, the proof of this solution to this problem. And that's all you have to really know. I mean, you can get away with doing the solution by separation each and every time you come across this form of equation. But it's often easier if you see, say, dy dt equals 3y. It's often easy enough to just go, well, okay, this is going to have an exponential solution. I'm not going to bother going through all my steps. I'm going to write the solution down by pattern matching. Right. The idea is that each time you identify this as k, right, and then the solution is y equals constant e to the kt. All right, so that's the solution by inspection of the exponential ODE. Now we had another ODE. This was a second order ODE. Now, some of you might recognize this as the simple harmonic motion. Equation. It says that the acceleration of an object is proportional to the displacement of the object. We're not going to worry too much about that. We're going to note that second prop 2, proportional, and the constant of proportionality is omega squared. Second derivative is proportional to minus, actually I should write the negative of 2 then. Okay, second derivative is proportional to the negative of the function. There's a couple of functions that have that property. The cosine and sine functions, right? That means that y is either a cosine or a sine, or as you'll see, it can be a superposition. You can add them up and get both of them. So what you just have to do is you have to just take care of this omega. So our solution by inspection y equals a cos omega t plus b sine omega t. You'll see this solution developed in greater detail when you look at the general techniques for solving second order linear ODEs. For now, we're just going to check that this solution works. Now, we know that if we're given a proposed solution and we're asked to check, all we have to do is substitute the solution, the proposed solution, into our equation, both sides. So I need to compute the second derivative of this function and check that it's equal to minus omega squared times the function itself. So let's go ahead and do that. So dy dt equals, this is the first derivative. So the first derivative of cos is minus sine. Now, I've got an omega here that I have to take care of. So remember function of a function rule. Here I've got the same thing. I've just got b derivative of sine is cosine. There's no minus. I've got the omega, so an omega pops out. T. So this is looking promising, right? I've gotten one of my two factors of omega that I expect. So let's do it again. Let's compute the derivative of this, which is the second derivative of y. Derivative of sine is cosine. There's no minus sign. I've got an omega that pops out, so this becomes minus omega squared a cosine omega t. Derivative of cosine is minus sine, so that plus sign becomes a minus. I've still got a b. I've got another omega that pops out, so now I've got omega squared because there's an omega there. This is sine. And clearly this rewrites to minus omega squared like so, which is minus omega squared y. Now that's what the equation says. So if we find a functional form of y that makes this equation true, we say that the ODE is satisfied by this solution, by our proposed solution. And therefore, indeed, that the solution is actually a solution of the ODE. We've verified that this is correct. So yeah, that's what I wanted to talk about. The summary is here, just right up at the beginning again. Whoops, that's some of a different video. By inspection, one can write this down almost immediately. An exponential solution, and also this. If you can't see it straight away, don't worry. There's always other techniques that you can use to extract the solution.